Work done under conditions of variable force. The formula is W equals the integral from a to b f of x dx. To demonstrate the work required to stretch a spring, we'll be using Hooke's law. Hooke's law is the force f of x required to stretch a spring x units beyond its natural length is given by f of x equals kx, where k is the spring constant. In our first example, a force of 9 pounds is required to stretch a spring from 6 inches to 8 inches. Find the work done by stretching the spring from its natural length to 10 inches. Using Hooke's law, f of x is 9. 9 equals k times x, which is 2. Using algebra, we will solve for k. K equals 9 halves. Formula, our f of x is 9 halves x. Its natural is 6 inches. 10 minus 6 is 4, therefore our limit is from 0 to 4. The antiderivative of 9 halves x is 9x squared. Now let's solve 9 of x squared over 4 from 0 to 4. Let's plug in our 4. That would equal 9 times 16 over 4 minus 0, because 0 times 9 it would give you 0 over 4, which is 0. 9 times 16 over 4 minus 0 equals 36 inch-pounds. For our second example, a uniform cable 30 feet long and weighing 60 pounds hangs vertically from a pulley system at the top of a building. A steel beam that weighs 500 pounds is attached to the end of the cable. Find the work required to pull it to the top. Here's our little drawing of a man using a pulley system, pulling up our 500-pound steel beam 30 feet. Work equals 500 times 30, which is 15,000 foot-pounds. Now let's set up our problem. The work of the cable is set up the integral from 0 to 30 of the distance lifted, 30 minus y, times the increment of force, which is force divided by distance, that is 60 divided by 30 equals 2 dy. To simplify the problem, we can pull the 2 out to the front. The antiderivative of 30 minus y is 30y minus y squared over 2 times 2 from 0 to 30. When we plug in our y, we get 2 times 900 minus 450. That equals 900 foot-pounds. Our initial work, 15,000 plus 900, gives us a total of 15,900 foot-pounds.